Alright guys, in Unit 9 we are shifting gears from solving equations, which we've been doing for the past 3 units or so. Unit 9 is all about prime factorization and then about finding the greatest common factor. So before we can find prime factorization, we need to review what factors are. So if you look at the first part, it just says to write all the factors of the number. Now if you remember, factors are the numbers that go into another number, or that a number can be divided by. So, for instance, any number can always be divided by 1 in itself. So for 18, I know 1 and 18 can go, are factors. Then I also want to test 2. 2 can go into 18 because it's an even number, so that gives me 2 and 9. Then I would try 3. I know 3 and 6 go into 18. I try 4. 18 can't be divided by 4, so I'm good. When it says to write the factors, you can put them down however you want, but then when you write your final answer, put them in order from least to greatest. So 1, 2, 3, 6, 9, and 18. You do need to include 1 and the number as factors. So again, factors are just numbers that go into another number. I'll let you guys do it for 2 and for 41. As you do that, I've got a couple of definitions for you, and this prime and composite chart goes with these definitions. A prime number is a number that has exactly 2 whole number factors, 1 and itself. So it's hopefully you noticed when you did number 3 above, which was 41, the only thing that goes into 41 is 1 and 41. So 41 would be a prime number. Again, notice we're talking about whole number factors. Other decimals could go into only where a composite number is then a number that has more than 2 whole number factors. So like when I did 18 or when you guys did 40, there was more than 2 factors, so those were composite. Prime factorization is writing a number as a product of prime numbers. So if you look at the definition, that means we're writing a bunch of prime numbers as multiplication, which we'll get to in a second. And then a factor tree, which you've probably done in the past, is a diagram that helps you write prime factorization. You might not have used it for prime factorization, but you've probably used it before. And then the table right here just has some examples of prime and composite numbers and the factors that they have. Notice all those factors are in order from least to greatest. So the next part is just all about telling whether a number is prime or composite. And again, we tell if it's prime or composite by how many factors it has. So for 15, I know 1 and 15 are factors, and I know 3 and 5 are factors. So since it has more than 2 factors, this is going to be a composite number. For 13, I know that 1 and 13 multiply together to make 13. Then I also know that nothing else goes into it, so that's a prime number. I'll let you guys do 25. Then if you move down, this is the bulk of what we're looking at, is writing prime factorization. So, like I mentioned before, we're going to use a factor tree to help us with prime factorization. So, when I do a factor tree, I'm going to start with the number I have, and then it's just going to work its way out to look like a tree. I'm going to put 2 numbers that are factors of 32. 2 numbers that when I multiply them together, I get 32. So in this case, I'm going to pick 4 and 8. Now, I'm going to keep my tree going until I hit prime numbers. So 4 and 8 are both composite. So 4 I'm going to split into 2 and 2. 2 is a prime number, so I can circle it to let myself know I'm done there. 8 is composite. 2 and 4 can go into it. 2 is prime, so I can circle it. 4 is composite, so I have to keep going. So I break that into 2 and 2. So once I'm at the point where all of my bottom numbers, if that makes sense, all my farthest down numbers are circled and prime, that's when I know that I'm done. Now I need to write this in prime factorization. Okay, my factor tree hasn't got me there yet. So what I'm going to do is write my numbers, my prime numbers, as multiplication. Okay? Because we said our definition of prime factorization was product of prime numbers. So I write all these out as multiplication, but then I need to put an exponent with it. What I mean by that is I'm going to write this as 2 to the 5th because I have 5 2's and I'm done there. Looking at 56, I'm going to split this into 8 and 7. 7 is prime, so I can go ahead and circle it right now. 8 is composite, so I've got to split it up. So I circle the 2, so that's prime. 4 I can split into 2 and 2, circle that, and I've got all prime numbers now. Now I need to write them as multiplication, and I'm always going to go from smaller number to biggest number. So I'm going to go 2 times 2 times 2 times 7. Now if you look, I have 3 2's, so I need to write that as an exponent. That's 2 to the 3rd times 7, and that's my final answer. Now, for both of these, you might have noticed there's other factors that go into the original number. And it doesn't matter what numbers you pick, because you'll wind up with the same answer if you do it correctly. So for like 32, if I had done 16 and 2 instead, so I would circle the 2 because that's prime. 16 I could break into 4 and 4. Both of those are composites, so I'm going to split them into 2 and 2. So if you notice, I picked different numbers to start with, but I would wind up with the same answer for 32, no matter what. So on the back side, we're doing the same thing. We have to make a factor tree and then write the prime factorization. We're just working with much bigger numbers. So for 180, I'm going to start by splitting it into 60 and 3. Again, I could have picked 2 and 90, 20 and 9, a whole bunch of other numbers. I'm just picking 60 and 3. 3 is already prime, so I can circle that. 60, I'm going to split into 3 and 20. 3 is prime, so I can circle that. 20 I'll split into 5 and 4. 5 is prime, so I can circle it. And 4 I'll split into 2 and 2 and circle both of those. So if you look, still doing a factor tree, this one just looks a little crazier because I picked a bigger number to start with. When we write the prime factorization, again, it needs to be in order from least to greatest. So 2 times 2 times 3 times 3 times 5. Then we need to write exponents for anything that's repeated, so that's 2 squared times 3 squared times 5. And that is our final answer. Number 4, I'll leave for you guys to do. The last part of this section, we're going to look at factoring monomials, which is the same thing. We're just adding in variables, basically. So the definition of a monomial is here for you. It's a number, a variable, or the product of a number and one or more variables, which is a whole bunch of words. If you look over at the table, it's probably easier to understand. So everything on the left is a monomial, everything on the right is not. If you notice, all the monomials are one big multiplication, one big product. The ones on the right are split by addition or subtraction. Okay, so we're looking at how to factor those monomials. So if you look at our first example, you have 8xy. My recommendation to you is that you take the number part first. So I'm going to write 8 and do my factor tree. So I'm going to split that to 4 and 2. I can circle the 2. 4 I'll split to 2 and 2. I can circle both of those. So when I write out my factoring, I'll have 2 times 2 times 2. And I also have an x and a y, all just written out as multiplication. If you notice when it says to factor, I did not write 2 to the 3rd. It didn't ask for the prime factorization, it asked to factor. So if you look at the second example, I'm going to start with 45 and split that up into 9 and 5. I can circle the 5 to prime. 9 I can split to 3 and 3, circle both of those. So least to greatest, so I have 3 times 3 times 5. Then I have 3 m's, and an n that I have to factor out as well. Number 3 I'll leave for you, and then the bottom is just some pretty basic review of solving equations.